And so, today we're gonna work on this worksheet 11 about polar curves. It's the last worksheet. So you have probably seen the solution that is posted on UMLearn, and then it has most of the information there. And I think I will just go over some of the difficult questions that might be hard to understand here. So for question 1, we need to sketch the following polar curve. Okay, and then you can see that the first one here, it's r equal to 1 over theta, where theta ranges from pi over 2 to 3 pi. So when you sketch a polar curve, you kind of choose a point, and then you rotate that point counterclockwise. But during you're rotating that point, you need to pay a very close attention to the distance from the point to the origin. Okay, so that is how we plot the polar curves. And for this question, we know that theta starts from pi over 2, right? We know very well that pi over 2 is corresponding to this angle right here. So you can see that the starting point is somewhere here, kind of on the y-axis. And as we said, when we rotate this point counterclockwise, we need to pay a close attention to the distance from the point to the origin, right? So the distance is this r here, and you see that r is equal to 1 over theta, is a reciprocal function. So as theta increases, the distance actually decreases. So you can anticipate that when you rotate this point counterclockwise, the distance gets smaller and smaller. So this point is getting closer and closer to the origin, right, as you rotate it. So you can see that there's a kind of a convergent circle like this. And your terminal point should be 3 pi. We know that 3 pi is on this side, right? So you stop here. And at the point theta equal to 3 pi, you have the smallest distance. And at your starting point, you have the greatest distance. So that is what this curve looks like. Okay, so that is our question A. And now we move on to question B, r equal to cos 3 theta. We need to firstly find out the Cartesian curve, this function in the Cartesian form, that is r equal to 3 theta, cos 3 theta here, right? The curve looks like that in the Cartesian form. So you can see that when theta is equal to 0, you have distance equal to 1. That is the greatest distance. And after, the distance is gonna decrease, right? And it decreases to 0 at the place theta equal to pi over 6. And it continues to decrease, right, to negative distance. And the greatest distance here is negative 1. So we can kind of use this Cartesian curve to plot our polar curve. We know that we start at 0, right? Theta equal to 0 is corresponding to this x-axis here, right? And you have distance 1, so you start at here. And now you gradually rotate this point counterclockwise, and you keep track of the distance. You see that distance actually decreases, right? And it decreases to 0 right at the place theta equal to pi over 6. So that's why you need this angle pi over 6 here. See, distance gradually decreases as you rotate this point. And it goes back to the origin right at the place theta equal to pi over 6. So that is why we have this one here. And after this theta equal to pi over 6, the distance becomes negative, which means that we need to flip this to the other side, right? So we go to the other side here, and then the distance continue to decrease, and it has the greatest negative distance at the place theta equal to pi over 3. So that's why we have this angle here, right? And since the distance is negative, so it's the other side, the opposite side of pi over 3. So it's here, right? At this place, you have the greatest distance, okay? And now we see that the distance increases back, and it increases to 0 at the place pi over 2. Okay, so pi over 2, we know that pi over 2 is here. But since we're working on the opposite side for the negative distance, we're working here. So you can see that this goes back to the origin, right at the place theta equal to pi over 2, but it's at the opposite side. That's why it goes back, right? And you continue to keep track of this graph, right? It says it increases to 1 again at a place theta equal to 2 pi over 3. So you can just go here, right? Increase your distance as you rotate counterclockwise, and you can see that the point reaches this greatest distance at a place theta equal to 2 pi over 3, right? And for the the rest of the graph, you can just continue this pattern to finish the whole graph, right? So it's like that. So that is our question B. And now let's take a look at this question C here. R equal to sine theta square theta. We have the square, so we need to decrease the power. We use the identity to write this as 1 over 2 times 1 minus cos 2 theta. And then we can plot this graph in the Cartesian form, which is right here, right? It's like that. It's not difficult to graph it. And now we transform this to our polar curve, the polar form. From here, you have distance equal to 0 at the place theta equal to 0. So that means you start at the origin, right? And as you rotate this counterclockwise, you need to increase your distance, right? And the distance has the maximum value 1 right at the place theta equal to pi over 2. So you can see that this point goes like that and has the greatest distance at here. That is the most far away point here at the place theta equal to pi over 2. But after this point, the distance is gonna drop, right, and drop to 0 right at the place theta equal to pi. So as you continue to rotate this counterclockwise, this point gets closer and closer to the origin, and it goes back to the origin right at the place theta equal to pi, which is at here. Okay, and you can continue this for the next half period, and you see that you can get the other one here, right? Just in the exact same manner, right? I mean, because the Cartesian graph I gave here has only the period from 0 to pi, right? If you continue to graph this, you see that the next period is exactly the same, right? So as you continue to rotate this counterclockwise, you get a graph similar to the graph above, right? So that is question C. Not hard to see that, how we actually plot these curves. Okay, so that is our question 1. Very simple, I think. And now let's move on to question 2. Question 2 is about the tangent lines, right? Vertical tangent line and the horizontal tangent line. We have done such a question in the last tutorial, but that was not in the polar form. So the only new things here is that you need to convert this to the parametric form from the polar form. So that is the only thing to do. And then for horizontal tangent line, you're looking for you're looking for dy over d theta equal to 0 and dx over d theta not equal to 0. Okay, so it seems that I skipped the question 1 here, so let me just say a little bit about that, right? So it's a tangent line that at this point theta equal to pi over 6, right? So you want to find your xy coordinate that is corresponding to this angle, right? So after you convert this into the parametric form, you're going to plug in pi over 6 in here, right, to find the this is the slope, right? And also you find your point. Okay, after you have your point and your slope, you plug that in to the point slope form to have your line. That is very straightforward, and it's also written in the solution. Okay, and then this is the horizontal tangent line and the vertical tangent line, right? Exactly the same as the one that we did in the previous worksheet, right? It's just that when you solve this equation, it gives you theta equal to these angles, and the solution here actually has something to do with the range of theta you chose, right? You can choose theta that is in the period from negative pi to pi, that is just one period, or you can choose theta to be from 0 to 2 pi. So this is not fixed. Okay, this is up to you. If you choose the period theta from 0 to pi, then the answer here will be different. Instead of having pi over 4 positive negative and then 3 pi over 4 positive negative, you're going to have pi over 4, 3 pi over 4, and then 5 pi over 4 and 7 pi over 4. So it actually depends on the range of theta you chose here. But regardless, when you plug these angles back into the equation, you don't have that many points, because this positive or negative pi over 4, even though the angles are different, they gave the exact same point here, right? This point is given by this one. Right? Just imagine that if pi over 4 is negative, you have negative angle, right? But this distance also are gonna be something else. So you can flip that point, and then you only have these 2 points there. And we will include that in the next question about flipping the angle. Right? And I also believe that we did that in the last tutorial, right? We mentioned that you can plus pi, and then it goes to the other side, the opposite side, and also you can put a negative sign in front of the radius, right? Kind of flip the radius, and also it goes to the opposite side of the circle. Okay, so but anyway, this question is I think very straightforward, not so difficult. That is our question 2. And now let's move on to this question 3. Evaluate the area of the region that lies inside one petal of the 4 leaves rows r equal to 2 sine 2 theta, and outside of the polar curve r equal to square root of 2. So we have 2 equations here, 2 polar equations, right? And I will name them. This is R1 and this is R2, just to distinguish them. And of course, to obtain this picture, we first need to know how to graph it, right? So we want to graph this one first, this difficult one. So now we have the Cartesian form of the graph here, which is easy to obtain. Okay, so this is one period, that is pi, right? Because you have the coefficient 2 here, so it's kind of the compressed version of the original sine function. And also you see that the greatest and smallest value, they are 2 and negative 2 respectively. And now, as I said, we're gonna turn this into the polar curve, right? At here, we see that when theta is equal to 0, we have function value equal to 0, which means that the distance is 0. So we start at the origin here, and then we rotate this counterclockwise. But from the the graph here, it tells us that the radius, the distance is increasing, right? And it has the maximum distance at the place theta equal to pi over 4. So that's why we need this angle pi over 4 here, right? As we rotate this counterclockwise, this point gets further and further away from the origin, and is the most far away at the place theta equal to pi over 4, right? And after this theta equal to pi over 4, the distance is going to drop to 0 at the place theta equal to pi over 2. Okay, so it dropped to 0, right, goes back to the origin, right, at the place theta equal to pi over 2. That is right here. Okay, and then it becomes negative. That means we need to go to the other side, right? So go to the other side. That means instead of going forward, we go to the opposite, right? So it's here, goes here, right? And it has the maximum distance at the place theta equal to 3 pi over 4. This is 3 pi over 4. But keep in mind that distance is negative, so it is the opposite of 3 pi over 4. So we have 3 pi over 4 here, right? And the opposite side is here. Okay? So it goes to the opposite side of 3 pi over 4. That is the maximum distance. And then they kind of go back to the origin, right? You have distance equal to 0 at the place theta equal to pi, right? So this is the opposite of the theta equal to pi because distance is negative, right? Pi is here, right? And then the other side, the opposite side is here. So it goes back to the origin at the opposite side of theta equal to pi. So the graph is like that. Goes here, right? And goes there, and then goes down, and then goes around, and go back here. Okay? And you can just follow this, right? And draw another period, and then you see that the rest of the graph is like that. So let's do one more time, right? You go to the pi over 4, right? And then go to pi over 2, right? Go back to the origin, and then you flip to the other side, right? Complete this leaf here, and then go here, and then go back. Okay, so it's like that. That is what this thing is like. Okay, and now we take a look at the other one. That is r equal to square root of 2. You see that this r is a constant, right? It does not have any restriction for the theta and angle theta. So as theta increases, you always keep the same distance, r equal to square root of 2. So you see that this is a circle, because on any points on the circle, they all have the same distance from the origin. Right? So this is the circle here. So after we now have the graph of these two curves, we can start to take a look at what the question is asking. The question is asking us to find the area that is inside the R1 and outside the R2. So that is the area that I have highlighted here, the green area, right? It's outside the circle and inside the leaf here. And how do we find the area? Well, we need to use the integration, right? And we need to know the upper bound and lower bound. We need to know which point we start from and which point we end, right? So these 2 points, they are the intersections of the curves, right? So we're gonna equate these 2 equations. We let this 2 sine 2 theta here to be equal to this one, right? Equate these 2 equations, and then we kind of find the solution theta, right? You can see that the theta is found here. It's equal to pi over 8, 3 pi over 8, which is corresponding to the starting point here and the ending point here, 3 pi over 8. So we take them as our lower bound and upper bound, and we kind of establish the definite integral to figure this out. that is 1 over 2 r squared, right? And we use the further curve to minus the inner, the closer curve. That is like using a larger value to minus a smaller value. Okay, so 1 over 2 r squared d theta, r1 minus r2. Okay, and then we plug in, right? And I believe you also have the solution, so it's clear that this integration is not hard, and then the final answer is 1 over 2. Okay, so that is our area. Okay, and that is very simple, I think. And I think the difficult point here is to understand how do we graph this curve, and then how we can see that the area is like that. Okay, so that is our question 3. And now we can move on to the next question. Question 4. Sketch the polar curve C with equation r equal to this 1 plus 2 2 sine theta. And as before, we're gonna firstly sketch the Cartesian form of this curve. Okay, so r equal to 1 plus 2 sine theta, right? If we didn't have this 1 plus, then it's just like that. So with this 1 plus, you just move the 2 sine theta, you just shift this curve 1 unit upward. Okay, so you have this kind of r equal to 1, just like the y equal to 1, a horizontal line here, and your origin is here, right? And here is your x-axis, namely the theta axis. Okay, so the curve looks like that. And now these points are the points that we need to pay attention to. We need to know our starting point, that is here. When theta is equal to 0, the r is equal to 1, right? So that is our starting distance. And then this is the highest point, which means that at this angle, we're going to obtain the greatest distance, 3. Okay? And after this, the distance is going to drop to pi. Okay? Drop to 1 at the place theta equal to pi. And then also it's important to know these 2 green points, because those points are the distance equal to 0. Okay, it drops to 0. We don't know what this angle is. We need to find this theta here. Okay, so we're gonna let this 1 plus this thing equal to 0, right? And then solve this equation, right? Sine theta is equal to negative 1 over 2, and we found these 2 angles, right? So now we know that at these 2 angles, you're gonna have 0 distance, which means that you need to go back to the origin at these 2 places, okay, the green points. And also we need to take a look at this, the lowest point here, that is where theta is equal to 3 pi over 2, right? This is a negative 1, right? So you can imagine the distance here is negative 1. Right? And then after this, you're going to go back to distance equal to 1 at the place theta equal to 2 pi. Okay, so after we understand this, we need to move on. Let's sketch our polar curve. We give these 2 angles here first. That is theta equal to pi over 7 pi over 6, and then this is 11 pi over 6. Okay, and then we start at here 0, right? At the place theta equals 0, you're going to have distance 1. So this is your starting point right here. And then the graph here says you're going to increase your distance, and then you will obtain your greatest distance at the place theta equal to pi over 2. So you're going to rotate this counterclockwise, and the distance is going to increase. You get further and further away from the origin, right, and go to here. So that is your greatest distance at the place theta equal to pi over 2. And after this point, you're going to drop the distance, right? They're decreasing, right? decrease to 1 at a place theta equal to pi. Okay, so you continue to rotate, but you get closer and closer to the origin right now. And here you have the same distance as where you started, right? Distance is equal to 1, okay, here. And after this point, the distance is going to drop to 0. It is continue to decrease, and this equal to 0 right at the place theta equal to 7 pi over 6. Okay, so you continue to rotate this counterclockwise, and you go back to the origin, right? You touch the origin right at the place theta equal to 7 pi over 6. Right? So you go back to here. And after this, the distance is gonna become negative, so you can imagine you need to flip to the other side, right? And then you have the greatest distance at the place theta equal to 2 pi over 3, 3 pi over 2. Okay, so you continue to rotate, but you go to the other side, which is here, because you were here, right? You go to the other side, it's here. And then 3 pi over 2 is here, right? But we're talking about negative distance, so you flip to the other side, so you should be here right now. Okay, so you continue to rotate, and here is the opposite of 3 pi over 2. That is your greatest distance, right? Negative 1, right? So this distance is equal to 1, as not as large as the previous distance 3, and is also clear on this graph. And now you continue to rotate, right? You see that the distance here decreases, right? And it decreases to 0 at the place theta equal to 11 pi over 6. 11 pi over 6 is around here, this dashed line. But we are talking about negative distance, so you should take a look at the opposite side of 11 pi over 6, which is here. So you can see that you go back to the origin right at the opposite side of 11 pi over 6. Go back to the origin. Now you are here. Okay, you are here. And for the rest of the parts, you just increase the distance again, and then you go back to your 2 pi, right, with your distance equal to 1. So that is your last trip. You go from here, you increase your distance, you go back to the place 2 pi, which is the 0, right, here, and then you complete this. Now you complete this curve, right? So again, you start here, right, and you rotate, have your greatest distance, and then I drop the distance and go to here, and then you go to the origin, and then go to the inner loop, and then you go down, right, go back to the origin, and then you start again, and then you go back to where you originally started. Okay, it's like that. Okay, so that is, I think, easy to understand. And now let's take a look at the question. Find the area enclosed by the inner loop, right? If you want to find the area, you need to know the interval for the inner loop here, right? We've just done that, right? You go back to the origin at the place theta equal to 7 pi over 6. So you should start at 7 pi over 6, right? And then you do the inner loop. You end it at 11 pi over 6. So this is your lower bound, and this is your upper bound. Okay, so we set up the definite integral with a lower bound 7 pi over 6 and upper bound 11 pi over 6. Okay, and you can also see that in the solution, this is not like that, is something else. And that was because the solution didn't choose this. Instead, it chose the negative 5 pi over 6. Well, negative 5 pi over 6 is from the previous period, not at the current period. You can choose that. The reason that the solution chose that is because it does not want us to have a very large angle. So if you start at negative 5 pi over 6, then you can end at here, negative pi over 6. Okay, so in that case, we're talking about the previous, the last period, the previous period, not this period, it's the period before. Okay, but that doesn't matter because it's a periodic function, so you can take whatever period you want. So now we take this, start from 7 pi over 6, and we end it at 11 pi over 6, and go through this computation, right? And it's not hard to see that this is the final answer. So that is the area. Okay. And the second question is set up an integral for the length of the outer loop. Okay. So to set up the integral, we just need to know the range of theta for the outer loop, right? So the outer loop is like that. You start here, right? Go back to here. But what we did was not like that. We actually started here from 0, right? So we go from 0 to this 7 pi over 6, right? And then we kind of need to skip the inner loop, and then we go from this 11 pi over 6 to the 2 pi. So in this case, we will have two separate intervals. So we don't want that. So instead of starting at 0, where we will miss the initial part of the curve here, we chose to start at a little bit earlier stage. That is, we don't start at 0, but we start at the previous period, the last period, that is negative pi over 6. Okay, so we start at here, negative pi over 6, and then we go to 0, and then we continue, right, and go to pi, and then we go to this 7 pi over 6. Okay, so that is why we started at here. And this is also also up to you to choose the period. If you don't like choosing negative pi over 6, you can go from here. Here is the ending point of the inner loop, that is 11 pi over 6, right? So you can start at 11 pi over 6 if you like, but the point you end is the next period, which is here, that is 2 pi plus 7 pi over 6. Okay, so you can choose that period as well if you don't like negative values. So here, just to clarify that, you don't have to choose this lower bound. You can choose 11 pi over 6 as your lower bound, but your upper bound will become 7 pi over 6 plus 2 pi. Okay, so that is just the range. Okay, and then this is just the formula for the length of the curve, right? And then you kind of go through this, and we actually don't have to evaluate it. So that is our question B. Okay, I think that is very intuitive. As long as you can see how this curve is formed, it's easy to imagine how we should set up the integral. Okay, so that is our question 4. And now we move on to question 5. Okay, question 5 I think is the easiest question. We even don't have to plot the curve because it's just asking the length. And then the reason why we plot the curve is because we want to get the range of theta. But now the range of theta is already given. So you can just let the lower bound, upper bound be the given endpoints here, and then set up the formula, right? And then go through the computation. And also this is also written in the solution. So I don't think there is any need to go over this again. So that is our question 5. I think very simple. It's just a substitution that we need to do here. But that is also in your solution. Okay, so I think we have finished all the questions here, and then this is a maybe challenging topic because it's different from the previous topic. But as long as you you're comfortable with how the polar curve is formed by thinking about what I've taught here, and then should be not hard. So I will see if you guys have any questions. Any questions?